Hi. We spent several lectures talking about conducting matter or conductors. From now on, we're going to talk about a rather different kind of material called dielectric material or dielectric matter. First of all, conductors are pretty much equivalent to a metal because one of the defining characteristics of a conductor is that the charges are free to move around according to Ohm's law, and as a consequence, there occurs perfect screening, and which results in a net electric field being zero everywhere inside a conductor. On the other hand, dielectric materials or dielectrics, in simple terms, has only incomplete screening. And incomplete screening naturally implies the lack of conduction. And the reason, actually, the connection between these two statements, the inability to conduct electricity and incompleteness of the screening, they go hand in hand according to hopefully the following simple argument. Okay, so let's start with the case where the material is conducting. Then you would anticipate this sort of Ohm's relation to hold, namely, whenever there is an electric field inside a conducting material, then there should be a corresponding flow of charge or current in proportion to the electric field. And in equilibrium, that kind of current must vanish, of course, which would only happen if the electric field all vanished entirely, which is a statement for about the perfect screening. And the very statement that in dielectric materials the screening is imperfect, such situation can only arise if this Ohm's law did not hold. And that will probably imply that there's no conduction at all inside a dielectric. In other words, dielectric materials are necessarily insulators, whereas perfects materials with a perfect screening are necessarily conductors or metals. So we see that these two words are used interchangeably in the literature, dielectric and insulator. In practice, I think they really mean the same thing, but for some reason, some people prefer to use the term dielectric over the term insulator. Okay, so instead of conduction, what's happening inside a dielectric material when you apply an external electric field? Well, what happens in response to an external electric field in a dielectric can be summed up in one simple word, that is the polarization. So I'm going to spend quite some time thinking about both the physical and the mathematical aspects of this quantity called the polarization. But let me first begin with a pictorial description of what the polarization is. So when you don't have any external electric field, you can think of the electric charge distribution of any atom inside a material as more or less spherically symmetric distribution of negative charge coming from the electrons surrounding the positively charged ion or positive charged nucleus. But when there's an electric field applied, there's a slight misalignment between the center of mass position of the nucleus and the center of mass position of the electron cloud. So you might see a situation like this where this displacement of the two centers of mass takes place. So when you have a negative charge over here and a positive charge over there, we already talked about this quantity called a polarization vector, which is the sum of the charge multiplied by the location vector and summed over all the charges in the atom or in the molecule. And from this picture, it's pretty clear that the polarization vector should develop more or less in parallel, in the direction parallel to the applied electric field. So P proportional to E is the first characteristic that you would expect from this simple pictorial consideration. But now I'm going to make a claim which is quite a bit less trivial. And the statement is that if the polarization vector is inhomogeneous in a dielectric material, then that inhomogeneity implies there is an extra charge or extra charge density induced in that material. So inhomogeneous polarization induces charge density. And the proof, I will try to develop the proof of this statement using various pictures and heuristic arguments. So I hope you can follow along with me. So for simplicity, I'm going to consider only a one-dimensional polarization vector. By one-dimensional, I mean the polarization vector points in only one direction, x direction, for example, and not in y or z directions. And that should be enough to make our argument clear. Now, and we're going to further assume that this amount of polarization is inhomogeneous. That is, this px is a function of x and changes with the position. So what does that mean? Well, first of all, think about this generic picture of a dipole where you have a negative charge placed here and the positive charge placed over there with a certain separation, which I should have written as d, not r. And the product of the displacement vector times charge is what we previously defined as the dipole moment. And such definition, of course, works very well for a single dipole. But for the dielectric material and its description, it's better to develop some thinking or some ways of thinking in the continuum picture, which is at first a bit trickier, but with a little bit of practice, you can probably develop some feeling to handle the continuum situation as well. So I'm going to try to walk you through this idea slowly by first beginning with this consideration. What if I take a chunk of charge Q and displace it by the amount D and put it over there? Effectively, by doing so, I have left a deficit of charge in the original location equal to minus Q and create an extra charge in the new location equal to plus Q. And that's as if I have placed a dipole moment equal to Q plus Q times D on top of the existing charge distribution. Okay, so just moving a charge from its original location to some other location is equivalent to creating a dipole moment inside that medium. Okay, and now think about what happens if I moved all the charges by the same amount. So let's say I move this charge over here and move the charge that used to be over here to the new location exactly by the same displacement vector d. And again, the charge that used to be over here is now moved to this location and so on. But since I move all the charges by the same amount, it's as if I took some crystal and just moved it, displaced it by the amount d, which of course creates no changes in the internal state of that matter. And certainly there's no extra charge accumulated anywhere, since all I did is move the entire crystal by a certain amount. So this is the boring situation where nothing of interest really happens. But it gets much more interesting if I move only one layer of charge. So here, let's say I initially had this array of charges, Q, 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 but somehow I decided to move only this chunk of charge by a distance d, but not move any other charge from its original location. All right. So then the consequence of that action would be that I get to have twice as much charge sitting in this region, and the lack of charge where there used to be some charge. Again, the effect is that of creating a deficit of charge over here and an excess charge over there. Okay, so this is an example of what happens if the charge displacement occurred in an inhomogeneous fashion. So some charges get moved, but others did not get moved. The consequence, as you can see from this simple picture, is that you end up creating some local extra charge over here, or some local extra charge over there. Now, let's try now to make this idea into a more concrete mathematical formula. So to that end, I'm going to define this function P, which is a product of the local charge density, which I assume to be uniform everywhere. And then I'm going to multiply it by this function, which I call the displacement function. So this displacement function tells us just exactly by what distance I'm supposed to move the charge that exists at the location x. Okay, that's the definition of this function d of x. Now, so what happens would be that the chunk of charge that used to live here at location x has now moved by the distance d of x. But the chunk of charge that used to reside in the block right next to it at x minus delta x, they also move, but by a different amount, d of x minus delta x. And because I assume that d is some function of x, there's no reason why d of x has to equal d of x minus delta x. That is, if I move this chunk by 1 centimeter to the right, I have no obligation to move this nearby chunk by the same 1 centimeter, but rather I have the freedom to move this chunk by a 0.9 centimeter instead. Now, in that case, the charge that left the old region would be the charge density multiplied by the displacement, d of x. But the amount of charge that tried to fill that void left by the charge that has gone by a distance dx is now rho times this function. Okay, and since these two d displacements are not the same, there might be a difference. And this difference is nothing but the net charge created at the location x. And since by assumption this delta x is a small quantity, I can tail expand this expression to first order in delta x and arrive at the expression that looks like that. And then I can push this uniform density inside the differential and realize that rho times d was nothing but my original definition of the p, and therefore what I have is the one-dimensional gradient of the p. Okay, and this and let's not forget the minus sign, and this is what creates the excess or deficit of charge at the location x. And I'm going to call that excess charge rho induced. Now, this argument hopefully can shed light on the fact that the derivative of the polarization with a minus sign in front is the induced charge density. Now, generalize this argument to a three-dimensional case where P vector can point in all three directions, and you allow inhomogeneity in the displacement vector in both x, y, and z coordinates. Then this derivative should generalize to the divergence. Hence, this relation seems to make sense. Okay, so in the next lecture, I will try to develop more theories of polarization based on this simple result. Thank you.